Hey folks, Eric Scheidel here, the HVAC Service Mentor. Hey, welcome back to the channel. I'm really glad that you're here. Today's lesson topic is going to be a little bit of a helpful in the field how-to tip, and it's called Why Your Thermometer Sucks and What You Can Do About It. Now, if you've been paying attention to my channel for any length of time, or if you know me at all, or if you've been in any of my classes, you know that I am all about measuring temperature. Measuring temperature is very, very important. And likewise, it's equally important to be as accurate as you can. And if you've taken my advice and you've gone out and got yourself a real nice thermometer of any kind, right? Say it's a little inexpensive little pocket thermometer like this one. Let's say you've got a digital multimeter that has a temperature function, or maybe you went all out and you bought an actual dual input digital thermometer like this one. And if you're anything like me, you probably go around measuring the temperature of things, which is great. And that's exactly what you should be doing. And if you've been doing that, you may have noticed that, well, shoot, none of your thermometers seem to agree with each other. And if you try to check it against something else, it doesn't agree with that either. So what's the deal? Well, the deal is your thermometer sucks. And I'm going to show you how to deal with it. Just stick around. Okay, so I hope you figured out by now that this is a little bit tongue-in-cheek, but it's actually very serious because, yes, your thermometers are inaccurate. And that can create some self-doubt. It can create some confusion, but there is an actual way to deal with it. Now, before I get too far, I wouldn't be doing my job if I didn't remind you, hey, don't forget to like this video, subscribe to the channel, and hey, leave a comment in the comments section and let me know your thoughts. Okay, anyway, back to the topic at hand. Okay, so one thing all of these thermometers have in common with one another is their sensing element, or in this case, it's a type K temperature probe, sometimes called a thermocouple probe. And they're recognizable by their little yellow, usually yellow, end that plugs into your meter with these two little slotted ends right here. This happens to be what is called a bead probe thermocouple, and it's got just this teensy weensy tiny little itsy bitsy little ball on the end. Boom, right there. That is the temperature sensing location. And this guy right here has one of those encased inside of this metal end right here. The clamp style probes, they also have the same kind of thing. And the problem with them is that they're relatively cheap. They're kind of inexpensive. I mean, how much do you pay for one? What, maybe 25 bucks at the most? That's not a whole heck of a lot. And they're inconsistent. If I were to get, and this is a fairly high quality one, this is an expensive one, but that doesn't matter. If I was to get a box of 50 of these things and compare them all together, none of them would agree with one another. The problem isn't so much the base unit. It's the probes. The probes are just inaccurate, and it's very difficult to get an accurate measurement out of them. Now, once you know what their offness is, or once you know what their error is, then you can calculate and you'll be really accurate. If you want to measure the difference between two temperatures, you can do that as long as you're not too concerned with exactly what those temperatures are, and you will have an accurate temperature difference reading. But there are a lot of times when you do need to have an accurate temperature measurement. Here's one great example. Say, for example, you're working in a healthcare facility, and the hot water temperature that comes out of the faucets has to be a very specific amount. And the facilities manager has come to you and said, hey, Eric, I need you to help me get my water temperature dialed in because the state came down and they audited our facility and they told us that our water temperature is too high, we're in danger of scalding people, and we need to get this under control. Well, you're going to have to be able to accurately measure that temperature to make sure that when you leave, it's dialed in correctly. Therefore, you need an accurate thermometer. And if you can't rely on your thermometer, that's a tough spot to be in, right? So the key is that you get a thermometer that can be calibrated. Now, here's the challenge. This guy can't be calibrated. None of these things, and this is a really inexpensive one. I think this one's from Harbor Freight. Doesn't matter. They're all pretty much the same. The field pieces, the Kleins, the UEIs, all those little, stick probes like this thing, they can't be calibrated. They can't be relied upon to measure accurately either. If you have a digital multimeter that has a temperature function like this little guy does, can't be calibrated, can't be accurate. You do have to move into this kind of a thermometer, which has two inputs on it. Some have one, some have two, some have four. But I, always would want to have two so I can measure the difference between two temperatures. And these thermometers can be calibrated. And I'm going to show you how to do that here real soon. But I want you to think about for a minute about how would you go about calibrating a thermometer? Well, what you need to do is you need to be able to compare the measurement that your thermometer registers to something that you absolutely positively know what the temperature is. Now that gets a little bit tricky. What are you going to use? Another thermometer that is also inaccurate? Now you're starting to see how this can be a little bit tricky. When I first got into the trade, my father worked in a facility that used certified glass tube thermometers in their laboratory, and he was able to get his hands on one or two of them. And he had these thermometers. They're probably, 18 inches long, mercury bulb on the bottom. No, not the red stuff, mercury bulb, because these are like scientific, laboratory accurate, crazy expensive thermometers. And he said to me, "Hey, Eric, do you want one of these for your work?" And I'm like, "Dude, that thing's going to last like 3.5 minutes. It's a glass tube. I'm going to break it. Probably not going to be able to use one of those either." Now, if I had one, I could use it to calibrate my thermometer with, but I don't. And I'm guessing you probably don't have one either. So what are you going to do? Well, we're going to use a really cool science feature to be able to do this. We utilize water in a lot of different ways in HVAC, and one of the things that we do is use it as a teaching tool to demonstrate how refrigerants work. And one of the cool things about water is that it can be found in 3 different physical states, right? It can be solid, ice, it can be liquid, water, and it can be vapor, steam. And it can transfer in between each one of these. And there is a very crucial temperature at which these transformations take place. Now, the one we want to focus on most is when water changes from a liquid into a solid or back from a solid into a liquid. Now, we could use the boiling point of water where it transforms from liquid into vapor or vapor into liquid, the condensing temperature. But the challenge there is that temperature will vary, and sometimes pretty considerably, depending on where you are and the chemical makeup of your water and some other things. For example, where I am, I'm at a higher altitude. I'm about 6,500 feet above sea level. My boiling point isn't going to be the same as someone's boiling point, say, who's in New Orleans. It's going to be different, and you can't really rely on that. But what you can rely on is the freezing temperature of water and also the melting temperature of ice. It's the same temperature. That temperature is 32 degrees Fahrenheit, pretty much anywhere you are in the world, and standard tap water doesn't have enough chemical weirdness about it to cause that to change significantly. And so what we want to do is we want to measure the temperature of ice water that's in the process of melting. One of the cool things about a substance that's changing state from, say, solid into liquid, as we have when we have melting ice, is that while it is in the process of doing that, and while we have solid ice and liquid water in the same place at the same time, and this melting process is taking place, that process takes place at 32 degrees Fahrenheit, period. It will not change. It will be 32 degrees. And so that is what we can use to have something that we absolutely know what the temperature of it is, and then be able to calibrate our thermometer to it. So for this thing, I want to do is I want to demonstrate. I've got these 2 thermocouple probes, brand spanking new out of the package, never been used before. Plug them into this thermometer for the first time, and let's see what they say. There's a little bit of a difference there, right? One's showing about 68.2, the other one's showing about 70. And therein lies our problem. If we need to accurately measure temperature, we don't know exactly where they are, but they're not agreeing with one another. We know that there's an inaccuracy here somewhere. So what I'm going to do is I'm going to take the two of them and twist them together like a bread tie. So now they are both in the same exact, as close as possible physical location. Now let me take them into the lab and I'll show you how to do this. Okay, so I want to do this on my old Playmate lunchbox here because I already ate lunch. And this thing could probably stand to be clean. And it's about the right size and shape for what I want to do. And the little bit of insulation that it has kind of might help the cause. So let me get some ice. That should be enough. Now let's get some water in here. This is just ordinary tap water. I'd like to shoot for about a 50-50 ice water mixture. Let that set. What we want to do is we want this to get to the right melting temperature, and that's going to take a little time. You know, that ice just came out of the freezer. It's at about 0 degrees. The water just came out of the tap. It's about 50 degrees. And it's going to take a little bit of time for everything to kind of gel. So I'm going to give it about 15 minutes or so. One of the things I'm going to do is I'm going to tape these thermocouples onto the screwdriver here just to make my life a little bit easier. There we go. Now I got a nice handy dandy stir stick with a temperature sensor on the end. Okay, some time has gone by and been sitting here waiting for this ice and kind of stirring it up a little bit. And one thing I'm going to do is I'm going to hit the min-max button on my thermometer. On this particular thermometer, the min-max will record the temperatures, and every time the temperature changes, it'll beep. Remember that the water and ice mixture will be at 32 degrees while the ice is melting. So we do want heat to kind of enter into this system, and while it is in the process of melting, the temperature is going to remain the same. So when this stops beeping and it stops moving, I can be reasonably certain that its temperature is 32 degrees. And it seems like we've gotten to that point now. One thing that's crucial, I do want to keep my probes moving. I don't want it to set on the bottom of the bucket. I don't want it to set on an ice piece. I want to keep moving and get a good standard temperature. So here we are. Check it out. I'm going to push hold on this guy. These thermometers are about 2 degrees off. One's a little more than the other. We got 30.1 on thermocouple 1, 30.5 on thermocouple 2. Let me take the hold away. Take away the min-max. Okay, now it's time to adjust our offset, this is called. Start with thermocouple 1 first, and it needs to come down. We'll do the second one. It needs to come up a little bit. I'll keep that screwdriver moving. Let's see where we're at. I think we can complain about that. It's about as perfect can get. Now, in the future, I'm going to do this on camera. I'm going to tell you, I'm going to label each one of these probes. So now I know that this probe must only ever go into slot 1, and this probe must only ever go into slot 2. And now they are calibrated for this thermometer device. I can't use them in any other thermometer device and expect them to still be accurate, but as long as I use them in this device, they will be accurate. And when these wear out and I get a new set and I plug them in, I'll just recalibrate like I just did and label them, and then I will be accurate once again. So those of you who have digital manifolds may wonder to yourselves, well, how does this impact me? Well, I'll tell you what, if your digital manifold has a Type K thermocouple temperature probe, and that would be one that has a little end on it like this one, that's a good question. I don't have an answer for you. I don't know the specifics about all the different manifolds out there, but hopefully your manifold is sophisticated enough that it has the ability to calibrate the temperature sensors. If not, well, you may be a few degrees off here and there on your superheats and your subcools. But now if you have a multi-pin connector like this one, this is from my Testo set, these are a different type of thermometer altogether. They're significantly higher quality. They work a lot better, and I'm going to show that to you right now. This thing will plug back in, which is always fun. For crying out loud, going in the wrong direction. They're keyed, but it's hard to see which way they're keyed sometimes for me because, well, come on. There you go. Okay, so I'm going to take both of these guys, I'm going to plunge them into the ice water, and let's see what they do. There is no calibration feature on this guy at all. These are these different type of probes. So the cool thing about these is they're both almost exactly the same, and they're both within less than half a degree with no need to calibrate Pretty neat. Okay, so the last thing that I want to show you is, you might be saying to yourself, well, this is great, Eric, but you know what? I just got this multimeter. It has this thermometer function, and that's my thermometer. I don't have the cash to drop on a whole new thermometer setup right now. Hey, I totally get it, and that's okay. So you need to realize that you may have some inaccuracy. So there's a couple things that you can do with that. So first of all, I want to just show you a feature called relative delta. Not all meters have a relative delta feature, but this one does. And there's this button right here that says REL on it. If you have a REL, or if you have a triangle symbol, that means delta, that means change in. That will allow you to see the difference between two different measurements. And a lot of the time, that's what we want to do, is we want to measure the difference between two different temperatures. So right now I'm going to show you the difference between the ambient air temperature, where I am right now, and the ice bucket. So I'm just going to hit the relative delta right here, and it's going to zero out. So right now a probe is in free air, and it's measuring 0. I'm going to stick it in the ice bucket. And when it stops moving, it's recorded the difference in temperature between the two locations. That looks pretty stable for the most part. Hit the hold. Boom. 47-degree temperature difference. You can do this on supply versus return, into or out of a convector or heat exchanger. You can measure lots of temperature differences this way without being really concerned about what the actual temperature is. So the other thing that you can do is just measure the temperature of the ice water Okay, that's about 2.4 degrees high. What I would do then is I would take my magic marker and write 2.4 plus 2.4 on this probe, and only ever use it with this thermometer. Now I know that whatever this guy reads is 2.4 degrees higher than what it actually is. And now I can do the math and rely on this to be an accurate thermometer, just knowing what its inaccuracy is and applying that. Hey folks, hey, thanks for watching. That is how to calibrate your thermometer. And now that we've done that, we can be certain that this thermometer is always going to be accurate every time we use it. But there's a special thing we have to take into account. Now that I have this calibrated, I can only use this thermocouple in this slot on this thermometer and expect it to be accurate. Likewise, this slot. If I switch them around, it might be different. If I take it out of this thermometer and stick it into a different one, it might be different. So for the life of these thermocouples now, this thermometer is calibrated for these thermocouples. And when I buy some new ones, I'm going to have to go back through the calibration process again. Now that I have taken the time to do this, I can be sure that my measurements are accurate and reliable, and I can count on that.